Hello everyone. So let me revise some of the things that we had discussed in the last class. We discussed about polarization. We saw that how an unpolarized light becomes a polarized light when you use a tourmaline crystal. Then we also saw that how we can do the same thing using Brewster's law. And then we discussed the Nicol prism that also does the same thing but in a more professional way. So we saw that this is a Nicol prism which is made by using the double refraction materials, uniaxial crystals, in which as soon as an unpolarized light enters, what happens that it gets separated into two lights. One is the extraordinary light, the other is ordinary light. Both are plane polarized, but they are polarized in planes which are perpendicular to each other. And then we do something such that the ordinary ray gets rejected and only we get the extraordinary ray coming out of the Nicol prism, which are plane polarized light. And we used these polarizers also as analyzers and saw that how we can check whether the light has already been polarized or not. After that we discussed, so this was the analyzer and polarizer and analyzer. After that we discussed something in which we showed that if you have two simple harmonic motions, one is in y direction, let us say, the other is in x direction, both are perpendicular to each other, and both simple harmonic motions, one is a sine omega t, the x is b sine omega t plus delta. So there is a phase difference of delta. Omega is same, so the time period and the frequencies are same, but the amplitudes are different. One is a, the other is b. A in the y direction, b in the x direction. So this is your y oscillation, this is x oscillation. Both oscillations are perpendicular to each other, and if they combine, then we saw that delta plays a very crucial role in deciding that what kind of motion of the resultant would be there. And we showed after mathematical analysis that when delta is 0, then we get another simple harmonic motion at an angle which is inclined towards x and y both, and the angle at which it would be inclined from x-axis would get decided by here tan inverse of a by b kind. So this is another simple harmonic motion with another amplitude. Amplitude would be given by a square plus b square under root in this case. And so the oscillation would be happening in this way. The oscillation will have the same omega, same time period, but in a direction which is inclined to both of them. But if delta is pi by 2, then we saw that the oscillation would be either elliptical in nature or circular in nature, and that depends upon the relation between a and b. If a and b are different, then we see that we would get an elliptical motion, whereas if a is equal to b, we would get a circular motion. And if delta is pi, then we get again a simple harmonic motion, but it would be inclined in the opposite way. And if it is in between the two, which is delta equal to 0 and delta equal to pi by 2, if I take delta equal to pi by 4, then we see that we get another ellipse, but this is a tilted ellipse, not a regular ellipse like this. This would be a tilted ellipse in which the major axis and minor axis would not be along the x and y axis, just as in this case it was there. And when it is between pi by 2 and pi, that is 3 pi by 4, again you would get a tilted ellipse but in opposite direction, something like this. So basically it means that we can create elliptical motion and circular motion if I use two simple harmonic motions which are perpendicular to each other and which have a phase difference of delta. Delta decides what would happen. So now we would try to see that how plane polarized light can be combined to get an elliptically polarized light or circularly polarized light using the same theory that we have discussed. We already know that if you have a let's say a uniaxial crystal, and in a uniaxial crystal we know that when an unpolarized light moves inside the uniaxial crystal, it gets separated into extraordinary ray and ordinary ray. But what is more important is that if you have optic axis, let us say, parallel to the boundary, something like this, then we have already seen what happens in that case when the optic axis is parallel, either this way or this way. I mean, this is the case in which the optic axes are parallel to the boundary. So in both the cases, if the normal incidence is there, then we get two waves, one for ordinary ray, the other for extraordinary ray. Both move in the same direction. Both move in the same direction, and that direction is the direction of incidence itself. Okay, so in the same direction it moves, but with different velocities, because the extraordinary ray and ordinary ray have different velocities. And so we try to use this to serve our purpose. Now, inside the if these are the optic axis, then we know that when it gets separated into two, the optic axis would decide that which one would be the extraordinary ray, because the oscillations in the direction of optic axis would be there for extraordinary ray. So this would be extraordinary ray, but the oscillations perpendicular to that would be for ordinary ray. And so both are moving, but both are moving with different velocities. That is more important. And let us say that if I take a case of negative crystal, so negative uniaxial crystals, if I take that case, then in negative uniaxial crystal we know that the velocity of extraordinary ray happens to be more than velocity of ordinary ray, and because of this what would happen, that the refractive index of extraordinary ray would be smaller than refractive index of ordinary ray. So when it would come out of this material, uniaxial crystal, then there would be a phase difference introduced between the two rays, the extraordinary ray and the ordinary ray. And how much would be the phase difference? That we can calculate. How can we calculate? If let us say that the thickness is T, then we can determine the optical path traveled by the two rays. So traveled by extraordinary ray would be nothing but mu E into T, refractive index into the thickness. And similarly, optical path traversed by O ray would be how much? Mu O into T. So the path difference introduced between the two rays when it comes out, so optical path difference introduced would be, since mu O is larger, so mu O minus mu E into T. This would be the path difference introduced between the two, that is the extraordinary ray and the O ray, when it comes out after traveling a distance of T in the uniaxial crystal. Now, if this path difference happens to be lambda by 4, lambda is the wavelength of the light that is being used. So if lambda by 4 happens to be mu O minus mu E by T, which means that if thickness is chosen such a way that mu O minus, that lambda divided by 4 into mu O minus mu E. If this much is the thickness, then what would happen? The path difference introduced would get lambda by 4, and phase difference, corresponding phase difference would be how much? Phase difference is nothing but 2 pi by lambda into the path difference, which is pi by 2. So if this much is the thickness taken, we can calculate this thickness, because if we know lambda, we know mu O and mu E, we can actually calculate T, and if I keep that T equal to that much only, thickness equal to that much only, then it would mean that the extraordinary ray and the ordinary ray will have a phase difference equal to pi by 2. Now since this is lambda by 4, this is known as quarter wave plate. It's quarter wave plate. Similarly, we can decide calculate the thickness of what we say is half wave plate. Half wave plate would be when the optical path difference introduced would be lambda by 2 instead of lambda by 4, mu O minus mu E into T, and in this T it would be lambda by 2 into mu O minus mu E into, that is, which means that this would be, thickness would be twice of this. Let me call this as T1 by 4 and T half. So if we want to create or construct a half wave plate, we'll have to keep this much thickness of the uniaxial crystal. If you want to create a quarter wave plate, we will have to construct a plate of this much of thickness. In this case, the phase difference would be how much? Pi. Phase difference would be pi. This was pi by 2, so this would come out to be pi only. So this is what is happening. Now how to, so we can use this to introduce a phase difference between the two rays. Now how do we use that? Now let's say I've made this for you. Let's say that this is your quarter wave plate. Okay, now if this is our quarter wave plate, what would happen? If I make an incident ray like this, I've made this for you. Let's say that this is your plane polarized light, in which the oscillations are like this. So this is, let's say, the electric field oscillations. Now, if this is the electric field oscillations, and since all of them are in the same plane, we can say that this model is representing a plane polarized light. What actually happens for a unpolarized light is that you get burst after burst. So after this much of the light is passed, the next light would come up with some another angle, in some another direction. When this would go out, the another set would come with some another direction. So that way the direction of oscillation of electric field would keep on changing, and it would change so fast that on an average it would appear as if that all the directions are there inside the, so sometimes in this direction, sometimes in that direction. So this is unpolarized light. But when it's polarized, then it would mean that all the bursts that you would receive would always be in the same direction. So the direction is now fixed. It would be fixed. So it would be same direction that the waves would be received. Now we can also analyze from here that what would happen if I get two plane polarized lights which are perpendicular to each other. So let us say that I have these two plane polarized lights, in these two plane polarized light, the oscillations are perpendicular to each other. So both are polarized in such a way so that the vibrations, the electric field oscillations are in perpendicular directions. Now if they are in perpendicular direction, and if it is something like this, then it would mean that both the waves have zero phase difference, because both of them are going to their maximum at the same time, both are coming to their main position at the same time, both are going to their minimum at the same time, both are again going to their maximum at the same time. So they are reaching their respective maximum and minimum at the same time, so we call that as zero phase difference. And if that is so, if they would combine, what would happen? They would combine means that this vector and this vector would combine. You can know, we know that we use the rectangular theorem of parallelogram to get the resultant, and resultant would be somewhere in this direction. In this case, in this model, actually the two vectors are of the same length, so at 45 degrees you would get the resultant like this. Okay, so two plane polarized lights which are having zero phase difference would result into another plane polarized light which is in the direction 45 degrees inclined to any of these. So this is another plane polarized light. But if you have a two plane polarized light with a phase difference of pi by 2, now how much is pi by 2? Pi by 2 would be actually that this whole thing is 2 pi. One full wave is 2 pi. So half of that is pi. So pi by 2 is this much. So if I can show something like this. So again there are two plane polarized lights, but the phase difference is now pi by 2. Now you would see that if I combine this vector, and there is nothing over here, so the vector would remain the same. So the field is only this. If you look at this position, again the second one is at its maximum, but the first one is at 0. So there is nothing over here, so the resultant would be the same, this field. So this field, this field, this field, this field. So this way it is actually only rotating from here, it gets rotated to this, it would get rotated to that, it would get rotated to this, again it would come to this and this one. So the combination of this is actually what you are seeing is that there is one single vector which is rotating across the direction of propagation, and this is nothing but your circularly polarized light. So it is something as if that if this is the direction of propagation, then if this is your electric field, then electric field is not oscillating in for circularly polarized light. It is just rotating like this. So it is not changing its value, the magnitude, it is just changing its direction. So it is doing like this. So circularly polarized light the electric field is just rotating like this. If it is elliptically polarized light, while rotating in one direction it would be a maximum, in the perpendicular direction it would be a minimum. Again it would reach to maximum, reach to a minimum, maximum, minimum. So this way you can visualize the elliptically polarized light. So there is a chance that if I can combine two plane polarized light, we can get an elliptically polarized light or a circularly polarized light. Now let us say that this is our quarter wave plate. Now if this is the quarter wave plate, and if I make a polarized light incident like this, now we know that since the polarized light is getting incident in the direction of the optic axis, so it would just pass through inside the uniaxial crystal, and only E ray would be inside this, because only E ray has oscillations in the direction of optic axis. So inside the uniaxial crystal you would not have any other ray but only the E ray. Similarly, if you have this kind of a situation, and instead of in that direction, now let's say we decide to make it incident in this direction. Now this is the direction in which the oscillations are perpendicular to the optic axis. So this again would get inside the uniaxial crystal, but only as an ordinary ray, because ordinary ray only has oscillations perpendicular to the optic axis. So if there is a plane polarized light, if I get an incident like this, you get inside the uniaxial crystal only ordinary ray. If you get it incident like this, what you get inside the uniaxial crystal is only the extraordinary ray, because the oscillations are in the direction of optic axis. But what would happen if I make it incident like this? Now if I am getting it incident like this, then actually a component of this would become extraordinary ray, and component of that would become ordinary ray. So inside the material, inside the uniaxial crystal, this plane polarized light would get divided into two plane polarized lights. One would be the extraordinary ray, the other would be ordinary ray. And if this is a quarter wave plate, then after coming out of the quarter wave plate, you would get a situation where the two extraordinary ray and the ordinary ray will get combined with a phase difference of pi by 2. And once you have a phase difference of pi by 2, you know that what you would get would be nothing but the circularly polarized light. The angle would actually decide that if the angle is 45 degrees, then this would mean that the component will have, both the components will have the same amplitude. And if the amplitudes are same, and then if they combine with pi by 2 phase difference, what you get is circularly polarized light. But for any other triangle, for any other angle of inclination other than 45 degrees, one of them would be larger, the other would be smaller. And when they combine after the phase difference of pi by 2, then what you would get would be nothing but the elliptically polarized light. Okay, so this is the way in which you can produce an elliptically polarized light or a plane polarized light, circularly polarized light, using a plane polarized light. So what you require is only a plane polarized light and a quarter wave plate. Okay, and the circularly polarized light, I can show you something like this only, not better than this. I couldn't get anything better than this, in which the electric field is rotating. It is not changing its magnitude, but it is only rotating while it's moving across in the direction of propagation. So, and the same thing would happen if you have a circularly polarized light, and if you make it pass through the quarter wave plate, then what would happen? Because if you have a circularly polarized light and if you make it incident on this, the circularly polarized light would get divided into two components. One would be one would be E ray, the other would be O ray, in which there is already a phase difference of pi by 2. But when it would come out, then there will be a phase difference pi by 2 again introduced between them. So total phase difference would become pi, and that is why what would happen? The cases we have already studied, that it would again become plane polarized light in some another angle. Okay, so a circularly polarized light, when it is passed through the quarter wave plate, it would become a plane polarized light. What would happen for an elliptically polarized light? It would depend actually, because elliptically polarized light, if you make it incident like this, in which the major axis and minor axis, they are parallel and perpendicular to the optic axis, then they would get divided into two components, and both will have a phase difference of pi by 2 here also. So when it would come out, it would again become a path difference of pi. Additional pi by 2 would get introduced because of this quarter wave plate, and so the phase difference between the two would again become pi, and you would again get a plane polarized light. But if you make it incident like this, then obviously the phase difference is not pi by 2, it is something else. So when it gets two component, one E ray, the other O ray, the E ray and O ray in that case would not be would not have a phase difference pi by 2, it would be something else. And so even if a pi by 2 additional phase difference is introduced because of this quarter wave plate, there is no guarantee that you would get a plane polarized light. So if you want to create a plane polarized light from an elliptically polarized light, then the criteria is that you must get the elliptically polarized light incident in such a manner such that the semi-major axis and semi-minor axis and semi-major axis, they become parallel and perpendicular to the optic axis. And once you have done that, then you are sure that the two components will have phase difference pi by 2 initially itself, and after coming out it will have an additional pi by 2, and you would get either 0 or pi, which would make the combination, the resultant, again a plane polarized light. I think we have covered the whole thing, and then we are left with the optical rotation. So in the next class we would cover the optical rotation and understand that how polarimeter is used to determine the specific rotation in those cases. Thank you very much.